Hello all, welcome. My name is Mehmet Akif Tütüncü. I'm a software engineer at IO, and today is my second day at my new work because until 2 days ago, I worked at Scala for Conductor, so it's an interesting time for me. Today I'm going to talk to you about a library I wrote called Effect, and I'm going to speak about mostly my approach and the lessons I learned during this process. And before I do that, I want to start with, you probably wondered this too, why another effect system? Well, I thought, why not? And this actually got inspired by the beautiful video series called ZIO from Scratch, made by Kit and Adam on Symposium. I wanted to understand these complex structures better, these effect systems, that magical things that we love and use. I wanted to also experiment with different techniques. I've been writing Scala for a long time, but this particular thing wasn't something I did before. I also wanted to be a library author, not just a user, because it also brings you another, point of view. So I named my library Effect because that's what it is. So I want to just briefly talk about what functional effects are. This audience probably doesn't need much about this, so I'm just gonna point to one quote here. This is actually taken from Reddit and written by John DeGoes. This was the first result that came up when I Googled what are functional effects. So I wanted to point out three important things about functional effects, that they promote immutability. They do the distinction between description of things and actual execution of things, and they also bring referential transparency to our programs. So the effect as a library. So this is a really basic, like homemade kind of functional effect library, and it has some powerful things that I think are powerful about error handling. And it is just with one type parameter. And it is actually mentally equivalent to the ZIO any effects.e my error type and A. So no environments in here anywhere, but the error type is kind of specialized, and it is this library is only bringing you a functional effect, not more stuff that some of the most popular effect libraries currently do. And this probably looks really familiar to you. That's how you are able to write an effectful application. You just compose effects. And this is another example showing you how to build effects. You basically call their apply methods. And once you are trying to build an effect that fails, you have this E type, which is something I'm going to talk about now. So yeah, that's a short example. So as I said, I'm going to focus on the error handling approach I took for this library. And to do that, I wanted to highlight what I think of errors. I tend to categorize errors in these three types. An actual error in our programs is the possible failure that we kind of expect. And these are usually our domain errors, which means that they are part of our application logic. And since they are things that we expect to happen, they are things that we use in our domain, I just call them errors. There are cases where people use exceptions for this, which I think is wrong. That's why I prefer to call them plain errors. And with errors, you can just write your program around it. They are just values to us. They should be values to us. So that's what errors are. There's also unexpected errors, which are actual exceptions, the unexpected stuff that can happen. And the important thing that I think is the characteristic for these types of errors is that they are unexpected and there isn't really much to do about them. We could maybe, I don't know, retry. We could ignore, which isn't something good, but they are unexpected stuff. An example could be IO exception, I don't know, SQL exception, etc. But the essence is that it is exceptional. It's not a value. It's not part of our application. And there is the fatal kind of errors that just blows things away, kills your program, which is beyond the scope. So based on this knowledge, based on this experience, what I want to highlight about errors is that we should treat errors as values, which luckily us Scala developers are something familiar with, and we do this all the time. And we don't want to write programs that depend on unexpected kind of errors and exceptions for our program control. And based on all this, I came into some conclusions. This was actually something I worked on before writing this library, that not all errors are similar, not all errors are the same, but in fact, in our daily lives, most of them have a certain structure, most of them are similar in certain ways. And to start with, the simplest thing, an error is actually some sort of message describing what is actually wrong. And it may or may not have some additional properties, usually semantically grouped in certain ways. So combining all these knowledge, I came up with this thing. It's super simple. It represents a very generic error that it gives you ability to model most, if not any kind of error that you may have in your domain. So I called it E, something super short and simple. And coming to effect, I wanted to incorporate this kind of error modeling and error handling into a functional effect, because when I first worked on this and created this library called E, I wanted to provide a way to have this kind of error handling for many things. It had a module for Java, a module for Kotlin, a module for Scala, obviously, and some additional interoperability, I would say, libraries for JSON serialization with stir-C and stuff. But that was only about error handling, and using this in a real application turned out to be somewhat not ideal. So I was thinking that if my effect system already had this built in, that would make things much easier. And when I had the idea to dive deeper into effect systems, I was like, I should build my E into this. So this is what brings me to how to build an effect system. And as I said, it is really inspired by ZIO from Scratch series. The very first thing that it taught me was to start with something very small. Declarative encoding, which is seen here, really helps with what I'm trying to achieve here, because I'm trying to build a functional effect I'm trying to build things as values, as representations, which are also descriptions of what I'm trying to do and not the execution. I'm trying to get the laziness by default. I'm trying to get the referential transparency. I'm trying to separate the description from the execution. So these are actual very first lines that I wrote. So I called it effect for any type A, and there is a way to run it to get an A. And since I'm going with this declarative encoding style, I need to have certain types of implementations of this. What essentially an effect does, what an effect can do, when you think about it, the first thing is holding a value, yielding a value. So there is a case called value, and to provide laziness, I used this technique of calling this, making this parameter by name. So it is lazy. Whenever you want to create an effect, you call its apply method, which, as we saw earlier, like you effect and in parentheses, you provide the value. And since we want this to be lazy, it is by name parameter. So in the representation of this as a case class, we cannot use by name parameters directly. So this is an anonymous function that doesn't really take any value. And to run it, which is the execution part, we just invoke it. So that's one thing. That's how I started writing this. Going one more further, we want this effect thing to be useful. We want to be able to represent values with this, and we want to be able to write programs with this thing. And what we do in writing our programs is that we write expressions, we write values that compose with each other. And the most natural, the first thing that we do is to sequence stuff, which is flat map, as we might be familiar with the concept. So in addition to run, an effect should be able to do flat map. And the signature is familiar to most of you, most probably, and how to represent this as another case of the declarative encoding we have is this, where we have two type parameters now for an effect of A, and for its success value going to an effect of B. And this is bringing us the ability to sequence things and compose things in the sequential way. How does it do that is, if we focus on the running part, we see that we are first running this current effect to get an A, and then calling F to get to the next effect. So things occur in order. Going forward, I want things to be implemented in terms of other things. I want to know what components I have are the core components, and what other features that I may get for free because I have other components are there. So I wanted to add the ability to map, which is just this actually. It's something that can be implemented in terms of flat map. So this is how I added that. Since I had flat map, I didn't need to add any more for cases, and I got map for free. Moving forward, how I added the ability to work with errors. So far, our effect was able to produce values and do them in sequence. So do it one value and use that to build another value and so on. To be able to fail with something, we already have a great tool in Scala, which is called either. So when I want my effect to be able to produce a value or fail, I make my run method now return an either. So when this effect runs, I either get the value I want or get an error. And this E now is not a type parameter, it is the E I showed you earlier. So also using the previous technique I mentioned, what is the most core thing that I need to be able to work with this effect, both with values and with errors? It is the fold operation. It needs to let the user handle all the cases that are available there. So to be able to build in the support for errors, I implemented the fold. And what fold eventually ends up doing is running the effect, getting that either, and calling the fold that either already provides with the functions that we get. Moving forward, getting the effect to have some asynchronous capabilities, I needed to introduce fiber, which is also what ZIO does. And at this step, things started getting more and more complicated because having the actual separation of description and execution in mind, I had the run method of the effect abstract and implemented it for each case. But trying to manage that state in different classes started to get really complicated. So for both performance reasons and for easier runtime, I would say, things are put in a single place, which is here called fiber context, which introduces this this notion of run loop, and it becomes this internal state machine, and it holds all the state that your effect is currently doing. What this also introduced is the continuation, because that's how the effect run loop moves forward. So you have one value and you have a continuation to do the next effect. So essentially what fiber brings is this run loop, and when you run your effect, now it doesn't really just invoke the run method of that particular instance of the effect, but it spins up a fiber which starts running. This is both to contain the complexity in one place, and another very important aspect of this is stack safety. Because I don't know if you could imagine, but if we compose a couple of effects like we see here actually in the first example here, what we are doing is a for comprehension, which is flat map, flat map, flat map. And we are creating a value first, then wrapping that in a flat map with another effect that creates a value, wrapping a flat map, etc. So this actually fills up the stack. If you try to build a big program with this, it doesn't have to be that big even, you end up with stack overflow issues, because that's what we are doing, stacking things. So introducing fiber and this notion of run loop actually moves all this from stack to heap, so that we are actually creating, using and removing values in memory, not with stack. So this makes things run in a stack safe fashion. And if we want to focus on the loop itself, what it is doing is simple, not so simple, but basic at least, state machine. As long as we are looping, we get the current instruction. Based on what it is, we perform our execution. So if this is a value, we just continue with that value, which means that we look at the continuations, and if we already have a continuation, we provide it with that value. And how we add continuations is by having flat maps and other sort of operations. If this instruction was a flat map, we push the continuation that is provided in that flat map to our stack and just move on. So as you can see, even at like this step with like 3 or 4 features, effect systems start getting more and more complicated. I don't know if you ever done this, but if you go to the implementation of ZIO with no or little prior knowledge of how effect systems work, it can get really frustrating to understand how things are built. So that's why I did this sort of experiment. And that's why I wanted to give this talk, to talk about the takeaways, the lessons that I learned from this. So one thing is that declarative encoding really helps you start writing something that has this separation between the definition and the execution. You can choose how to model things, but it lets you start by describing things, and that really helps building such a tool. So another thing is being lazy with the values and the deferring of the execution. So that helps you write correct programs with referential transparency. So you have the confidence to extract things into variables, do some refactoring, that sort of stuff. So another one of the more important points of this talk is that it taught me to think about this kind of stuff to build a library. You need to be concerned about your public API. I found myself asking these 3 questions to myself whenever I'm doing something in this code base. So I am thinking of adding something. I ask myself, would the users actually need this? How many different ways, in what cases that my users would use this? Another question is that, would this change in the future? Because this is going to be a public API of my library. And if this is going to change in a way that's going to break things in a future version, I need to think more about this. And the last item, can this thing be implemented in terms of other things? Just like we saw in implementation of the map, it can be implemented in terms of flat map, so that I don't need to actually have another case for map. That's a simple example, but that's one of the core ideas that I followed during this. And lastly, managing concurrency is hard, especially when you're trying to build such a system and you want the concurrency and async behavior of this to work correctly. The initial tries that I made seemed to work. Then I tried to just tweak it a little bit, and everything just blew away. So concurrency is hard. And what's next for this library? I mean, what I want to have about this in the future is more and better documentation, because it lacks user documentation, especially. It has some Scala doc. The members are documented, but how can you use this? What can you do with this is not documented yet. More modules for extra stuff, like interop with other libraries, convert this to and from futures, ZIOs, CATS effect, etc. Obviously fixes and new features. And there's the project board on the GitHub for this project, where I want to keep track of things. And thank you very much. If you have questions. If you have questions, you can ask them on Discord or find me. I'll be around. Thank you.